Hey, good morning everyone. It's Miss Packard. I hope you're doing well, and I am glad you're watching this video. Today we're going to be talking about parts of an exponential function. So the objective is that you will be able to identify and interpret parts of an exponential function. So real quick, let's go over what we've done over this pandemic online learning. So we started with linear versus exponential. And then we talked about the definition of a log or a logarithm. Then we talked about data, specifically exponential data, and how that looks on a log scale. And now we're going to be talking about exponential functions. And tomorrow we will be doing solving exponential functions, right? So we remember from when we were in school that solving exponential functions has a lot to do with logarithms, because logarithms and exponentials are the inverse or the opposite of each other. Okay, so this whole online learning we've been doing exponential and our logarithm unit, and those exponential and logarithmic functions are hand in hand. They're tied together. They can't be separated because they're exact opposites of each other. All right, so today our agenda is to watch this video. You're going to take some notes on the parts of an exponential function, and then we're going to do an example with actual data about the coronavirus. All right, our classwork today is a Google form in which I'm going to ask you to identify and interpret parts of an exponential function. All right, so let's get started. This is a basic exponential function. So what I've got here, and I want you to be writing this down, f, that's my function notation, right? F of x. F is the function. And we would say that x is our input, right? Now, another way you might see an exponential function would be y equals. Then we would say y is the output, right? Or f of x, that whole thing would be our output in that notation. Okay? Our next part is this a value. A times b to the x. So we've seen b before. B is always our base. Easy to remember, B for base. But A is always the y-intercept. And what happens if there is no A value? That would mean there's an invisible 1, right? If we don't have an A value. And then, of course, we have our x in our exponent, which will still be the input. Right? We know x is the input. Now I want to give you another way you might see this. You might see a and then parentheses b to the x. This formula is the same exact thing as this one. It's saying all the same things. We still have a times b to the x. Okay? The x is still only going to be the exponent for b. Right? So we are not, does not equal like a to the x, b to the x. So we will not be doing that. Otherwise, everything else is still the same. We still have our y-intercept, our b base, and our exponent, which is our input. I can say that again, too. Okay, so these two things are totally equal. We do not ever want to see the exponent applied to both. That's not one of our properties of exponents. Okay, so let's get to our example. You should recognize this graph from yesterday, and this is data that I collected myself from a website that I can link. But basically, this is the total number of COVID cases in the US starting on March 1st. So day 1 would be March 1st. And I've cut this one off at March 31st. So the data you looked at yesterday, I think went up until about April 9th or 10th. But I've cut this off at March 31st because in April is when we really started to see social distancing take effect. Okay, and what I did is in Excel, I fit an exponential trend line to this data, and I asked Excel to give me an equation. So this is the equation that Excel gave me, and I'm gonna write this down here. Excel, and I set my y-intercept. So that was not the original y-intercept. But once I asked them to give me that y-intercept, my equation is y equals 100 e to the 0.2419. Now, e is a special little number, okay? E is kind of like pi. You know how pi equals 3.141592, that keeps going? E always equals 2.71. Oh, I don't remember the rest. It keeps going on as well. So what I'm going to do is I'm going to rewrite this equation and make this just a little bit easier for us to use for this example. Okay, so I'm rewriting this equation as y equals 100, and I'm going to say 2.71. Oh, and I forgot the x up here. Whoops. And I'm going to round to 2.4x. Okay? So what we're going to do is identify the parts of this exponential function. So if I refer back to my notes, I'm going to look at my notes and I'm saying, okay, so I've got the y form with the parentheses. So then I say, okay, y, that's my output. And in this case, y is the vertical axis. Well, y is always the vertical axis. And what is represented on the vertical axis for this graph? I'm going to look at my title. It says total COVID-19 cases in the US, March 1 to March 31. So really, this graph needs some labels. So I'm going to label my vertical axis. This is total number of cases. And it's only in the US. Okay, and then my x-axis, or my horizontal axis, is the day. And we're starting at March 1st. So I'm going to say days since March 1. Or the number of days since March 1. So if we're at 5, for example, 5 days since March 1 would be 1 plus 5, so that would be March 6th. And that would keep going, right? So if this is my y-axis, and this is my x-axis, I'm really going to label this formula, okay? So y is going to be total number of cases. Total number of cases. 100. If I look back in my notes, that is going to be 100 is my A value, and A is the y-intercept. Okay, so 100 is my y-intercept. Now, what does that mean? If it's the y-intercept, that's the number of cases on day 0, right? Because a y-intercept is whenever x equals 0. So we could write a statement about that says, okay, according to this function, there were 100 cases on, and if day 1, oh, I think I explained this wrong earlier. Day 0 should be March 1st. So day 5, oh yeah, is March 6th. Okay, I did explain that right. there were 100 cases on day 0. So if this is number of days since March 1st, day 0 would be March 1st plus 1. So that's 100 cases on March 1st in the US. All right. So the y-intercept is the value on the first day in the data, or the 0 value for the x-axis. Our x-axis just happens to represent days as our units. All right, we've got a base of 2.71. So this is our base. But what does that mean? The base. Now think about if I had a base of 2 to the x, right? That means whatever my x value is, that's how many times I'm multiplying 2 by itself, right? So we actually have to do something a little different because this one's 0.24. X. 0.24. This number means that, and since we know x is number of days, we said that before because the x-axis is number of days. So x is number of days. If x is 1, then this value will be 0.24. So what happens is every time we increase by our x value, we still have to multiply it by 0.24. So this decimal, if I'm multiplying every x value by this decimal, means, and it's really close to 0.25, which would be 1/4. So this means that every 4 days, the number of cases increases geometrically by times 2.71, our base value. Now, how did I get 4? What I did is 0.24 is really close to 0.25. 0.25 times 4 equals 1. All right? So since 0.25 times 4 equals 1, I'm saying that 2.71 every 4 days will be increasing by, so every fourth day will multiply by 2.71. So really, I needed 4 days, and then I'm keeping that times 0.24, which I rounded up to 0.25, which isn't mathematically precise, but we are giving a quick estimate of why I'm saying about every 4 days the number of cases is increasing by times 2.71. Okay, so that means if I look at the data, I'm going to look at my graph up here again. So let's say we look at day 20. Day 20 is under 20,000. Day 24 is over 40,000. So let's say this is about 45,000. And let's say day 20 was about 17,000. And I'm just estimating here. And if I multiply 17,000 times 2.71, yeah, I get about 46,000. So we've confirmed what I've just hypothesized, which is every 4 days, the number of cases increases geometrically by times 2.71, which is what our formula is telling us, right? And our starting number, we started at 100. I'm not starting at, February, whenever the first case was, because it was a very slow increase for a while, right? Okay. There's just one more thing I want to show you. Please let me know when you have questions on this. I really miss hearing all your questions. But the last thing I want to show you is we're going to go to why is social distancing important? And we're going to use math because I love math. And Math can't lie. Okay? Why social distance? So we have this formula, right? I took my formula from my other page. That is y equals 100 times 2.71 to the 0.24 times x. All right? Right now, today I'm making this video on April 16th. And I looked on Wikipedia this morning, which is very reliable because they're giving the daily update. And on Wikipedia this morning, there were 644,000 cases about in the US. Okay, now let's figure out what this number would be if we didn't social distance, and we're following this model. So this is the original exponential curve until March 31st. So I'm using the data up until March 31st to predict anything after March 31st. Okay, so April 16th, let's think, how many days is that after March 1? Well, it's 16 days after March 31st. So if I add 16 to March 31st, or 16 plus 31 would be day 47 on this graph. So we're going to say x equals 47 and substitute this value into my equation. So I'm going to have y equals 100, 2.71, 0.24, and now I'm substituting in 47. All right, so let's do some math in the calculator because I can't do that in my head. So I'm going to say, okay, day 47 times 0.24. Okay, so I get 11.28. So now I'm going to rewrite my whole equation, 100 times 2.71 to the 11.28. Okay, now order of operations, PEMDAS, I'm going to do exponents before multiplication. So my next step is y equals, I'm going to do 2.71 to the, so I got to make sure my screen lock's not on. And in order to do my exponent, I flip my calculator and do the x to the y button, and it's 11.21, is that right? Oh, 11.28. Okay, so I get 76540. So I have y equals 100 times 76540.9. Okay, so now I'm going to multiply this by 100. And I'm going to get, okay, y equals 7,000. What? Is that right? This number seems huge. Let me try this again. 76540 times 100. Wow. 7654000. That is absolutely crazy. So this model is telling us that if we hadn't social distance and we continued to grow this much, or by this, following this exponential model, we would have had 7 million cases of coronavirus in the US at this point. So this is showing that social distancing is actually really effective, right? So we're comparing 7 million to only 644,000 cases today. And that's what we're talking about when we're saying flattening the curve, right? We're comparing our exponential model, right? Originally we have this exponential model, but what we are seeing because of social distancing is that this is stopping and we're slowing down, right? We're still growing, but we're slowing down. Still growing, but slowing down, and eventually we're going to come down the side of it because of social distancing. But if you do the math, you could see we could have been all the way up here instead of this slow value that we've got here. Okay, so to reiterate, please stay home. I know it's hard. Keep up with your schoolwork, but please, please, please stay home and wash your hands. All right, see you all later. Bye.